In this video, I'll explain to you all three of Newton's laws of motion. Now, before explaining to you the first law, I have to explain to you the concept of forces. Forces are everywhere in physics. They're fundamental. Now, a force is basically some kind of push or pull on an object. This might be you pushing the door open. That would be a force that you're exerting on the door. Now, if an object is at rest, to accelerate it in any direction at all, always a force is required, a force of some kind. This leads into Newton's first law, which states that every object at rest will stay at rest, and every object at motion will continue in motion at the same direction, at the same speed, as long as there's no net force that acts on it. Imagine for a second that you have a magical frictionless surface with no friction at all. You have a box. According to Newton's first law, if you don't touch the box, what happens to it? It's going to stay at rest. It's not going to move. It's just going to stay there for infinity. If you shove the box and you move it in this direction, what happens? As long as there's no net force that gets acted on it, it doesn't hit something, there's no gravity or air resistance, this box will move indefinitely in this direction at this same speed. It will never slow down, it will never stop. However, in real life, obviously, there's things like friction and air resistance and gravity even. So when you push something, it doesn't move forever. That means to push an object, you must exert a force greater than the friction and any other forces acting against you. The tendency of an object to stay at the same velocity or at rest, we call that inertia. Let me introduce to you a concept called inertial reference frames. So imagine this is you and you just went shopping, so pushing a shopping trolley, and you just bought a really yummy watermelon. When you push the car forward and then you stop, then from your perspective, from your point of view, you see the watermelon accelerating toward you. It rolls toward you, even though there's no apparent force acting on it. But it's supposed to stay at rest, right? Because an object at rest stays at rest. So that means the first law doesn't hold in this reference frame. This is what you call a non-inertial reference frame. So to know if a reference frame is inertial or not, just check if the first law makes sense, if it holds up. That was it for the first law. But before explaining to you the second law, I have to explain mass. When it comes to mass, there's a common misconception. Mass and weight are not the same thing. This is because your mass is the same everywhere. If I teleported you to Mars, you might be way lighter. Your weight would be less. You'd be bouncier and floaty. But your mass would be the exact same. You have the same amount of matter in you. That's because weight is the force of gravity. It is the pull of gravity. Mass is, however, the measure of an object's inertia. What does that mean? Well, take a car and a tennis ball moving at the exact same speed. It's much harder to change the velocity of the car. You need more force. That is because the car has more mass. Now, mass uses kilograms globally. That's what the global SI system uses. So in every video and this video, I will be using kilograms. Now that you understand the concept of mass and how weight and mass are different, I can explain to you Newton's second law. If you remember the first law, it states that an object will not change velocity at all. But what if an external force is exerted on it? Well, let's say that your particle is moving in a straight line and you decide to exert a net force in the same direction. Then your net force, well, it would increase, right? But what if I exerted force in the opposite direction? What do you think might happen to your net force? It would decrease. What if I did it in a different direction, like this? Well, the net force would change direction. all of these are in some way an acceleration. So we can conclude that net force causes acceleration. Let me give you an example. Imagine a space shuttle and you want to launch this space shuttle into space. You got thrusters, you got wings. When you launch it with a certain amount of net force, it accelerates to 500 meters per second. Now, if you exerted twice the net force, if you launched it twice as hard, what do you think happens? It would reach this speed, 500 meters per second, in half the time. If you tripled the net force, then it would reach it in a third of the time, and so on and so on. But that's not all. The mass of the spaceship also matters. Because if the spaceship is way heavier, then the acceleration would be slower. That means that the more mass an object has, the greater the mass, the less acceleration you can achieve for the same amount of force. This leads into Newton's second law. Now, what I'm about to say is the second law in words, and it's pretty long, so I recommend you get the cheat sheet that I made for myself that you can download in the description for free. It has everything you need to quickly reference these laws and formulas. Now, the second law states that an object's acceleration is directly proportional to the net force acting on it, and is inversely proportional to the object's mass. The direction of the acceleration is in the direction of the net force acting on the object. Let's break this down. The acceleration of an object being directly proportional to the net force makes sense, because the net force, well, more net force means more acceleration. When we say inversely proportional to the object's mass, that just means the more mass, the less acceleration. And finally, the last part, the direction of the acceleration is in the direction of the net force acting on the object. That's pretty straightforward. We can write this law in equation form, and in equation form, it would be acceleration equals sigma f over m. Don't be scared if you haven't seen this symbol before. What it means is sum of. That's all. So sigma f means the sum of all forces. Now this is your acceleration and this is your mass. When you rearrange this equation, you get the famous F equals ma, which you probably have seen before. This is one of the most fundamental equations in all of physics. The relationship between force, mass, and acceleration. Now, in SI units, so if you remember the SI global system, we use newtons to represent force. Now, newtons we write simply as N. So the more newtons, the more force. Mathematically, 1 newton is the force you need to accelerate a 1 kilo object at 1 meters per second squared. So that means when you multiply kilograms and acceleration, you get newtons. To help you really understand this and to make it click, let's go through an example. Let's estimate the net force you need to accelerate a 2,000 kilo truck. The first step is let's take our equation. This right here is your net force. So we just have to plug our things in. If we assume that the truck accelerates at 5 meters per second squared, then that means we can plug our values in for mass, which is 2,000 kilos. If you remember, mass is always given in kilograms, multiplied by acceleration. And since kilograms times acceleration is newtons, then our answer is 10,000 newtons. So you need 10,000 newtons of force to accelerate this truck. Now, what if instead of a truck, it was a 200-gram orange? How strong would you need to be to accelerate this orange? Let's do the same thing. F equals ma. The net force needed is equal to 200 grams, which we're going to convert to kilograms. So 0.2 kilograms, because we want our units to be the same dimension, right? Multiplied by the same acceleration. Let's say accelerates at the same speed. This means you get 1 Newton. So that means the truck was 10,000 times harder to accelerate. How about a real problem? A real problem with numbers and stuff. Well, imagine a driver driving at 30 meters per second and his car is 1500 kilos. He brakes and he stops in 55 meters. What is the average net force required to bring the car to its stop? Okay, let's do some thinking. Let's think about what we have. We have his speed, his mass, and the distance it took for him to come to a complete stop. What are we missing? Well, we're missing his acceleration, or I guess in this case it would be deceleration. Let's select the kinematic equation that works best, which in this case is this. Now, I'm sure you remember this from 1D kinematics. This is the equation for velocity when time is unknown. Let's plug in our values. So his final velocity was 0 because he comes to a complete stop. His initial velocity, 30 times 2 times A times displacement, which is 55 meters. Do your stuff, rearrange, and you get A roughly is equal to 8.18 meters per second squared. We found his acceleration. Now if F equals ma, then that means the net force is equal to mass multiplied by, let's take this acceleration, 8.18. And you get the answer 12,270 newtons. So for a car this heavy to come to a full stop in 55 meters, then you need this much force. You might have a question. Why don't we say negative? Because it's deceleration, right? Well, if you got negative, then it would be negative force, which works depending on your reference frame. But for simplicity, I just use positive numbers. You still get the value you want. Really briefly, imagine your melon cart again, right? You have your shopping cart with a melon. The melon accelerates toward you even though the net force is 0. So this law doesn't work in a non-inertial reference frame, because how is it accelerating when the force is 0? Moving on to Newton's third law. I might sound like a nerd, but Newton's third law is my favorite. When you look at real life, you can say that any force is exerted by another force. For example, if you punch someone in the face, then it's a force being exerted on this guy's face. Force of his head moving backwards is caused by the force of your fist moving into his face. So you can say that each force is caused by another force. However, Newton, with his genius megamind, realized it's not so one-sided, it's not so simple. Because when you punch his face, clearly something is stopping your hand. Your hand comes to a full stop when you hit his face. Your hand speed is rapidly reduced to 0. So this means that your hand must be exerting a force on the guy's face, and the guy's face must be exerting one back. This leads into the third law. The third law states, every action has an equal and opposite reaction. So whenever one object, your fist, exerts a force on the second object, his face, the second object exerts an equal force back in the opposite direction of the first force. Let me give you a more real example. So take your hand, and if there's a wall near you, let's say that's your wall and this is your hand, push your hand into the wall. The harder you push, the harder the wall pushes back. So you push into the wall. This is the force of your hand, but the wall pushes back equally as hard. The harder you push, the harder the wall pushes back on your hand. That's why the wall doesn't move. If you really push really hard, your hand might even start to hurt. That's because there's just a lot more force. Here's another conceptual example. Let's say you're skateboarding. Right? This is you, and here's your skateboard, and you stand next to a wall. When you push off the wall, you start going backwards. because the wall exerted a force back on you. The harder you push, the further you will travel in the opposite direction. Even when you're walking, the ground is exerting an equal and opposite force to push you forward. Your foot pushes backwards on the ground, and the ground pushes you forward in an equal magnitude. Here's a big misconception. Let's imagine a hill. This is you. And you're pushing a giant boulder up the hill. You might think, if there's an equal and opposite reaction, how does the boulder move? Because if you're exerting a certain force on it, and it exerts an equal one back, how is it meant to move? Well, the thing is, that's a misconception. Sure, the boulder does push back on you, but that's on you. You're the one who feels it. The boulder still feels your force. Your force still moves it. The force it exerts back the equal reaction. You're the one who feels it. The boulder doesn't get affected by the force it's exerting. It gets affected by the force you're exerting. It's on different objects. For every topic I cover, I like to create a free cheat sheet, and I use them myself as well. So if you want your own with all the formulas you'll ever need in one place, then go sign up in the description.